Hybridization is another way that we explain bonding in the valence shell, and it is one of our more sophisticated ways of explaining bonding, and it seems to predict a lot of things correctly. So this model is a pretty good model. If we look at methane, which is carbon with 4 hydrogens on it, we find that we have 4 bonds attached, and the carbons are tetrahedral, and they're all identical. They are at 109.5 degree angle from each other. They all have the same bond strength, and they all have the same bond length. I cannot do that with these orbitals over here directly, because I have one orbital that's different from the other 3. And if I try to overlap these with some hydrogens, then what happens is you get one bond that's different from the other 3. So what do we do to explain this? What we do is we do it with something called a mathematical hybridization, where they take and mathematically cut these up into quarters and then recombine 1/4 of the s with 3/4 of the p orbitals. And when we do, we get an 4 sp3 orbitals. They're shaped like this down here. We are not concerned with the small end. It's too small to enter into bonding. We're concerned with the large end. And when we do this mathematical hybridization, we find molecular orbitals, or excuse me, atomic orbitals, that actually point to the corners of the tetrahedron. And so it predicts how bonding is going to occur very well. If I go and I look at a carbon that has these 4 sp3 orbitals on it, and I bring 4 hydrogen s orbitals, they can bond and make 4 equivalent bonds, which explains very well what we see in our test. Okay, so this is how we will, these are 3 different models of showing how we draw the carbon with the 4 equal carbon-hydrogen bonds. And if I look at this, they all have the same strength and the same length, and so it's explained well with 4 identical sp3 orbitals. Ethane, we can explain its bonding. Ethane is down here, 2 carbons surrounded by 6 hydrogens. If we hybridize each of those carbons, they can push together, and we can get a sigma bond right here of an sp3 overlapping with an sp3, and then the hydrogens can come and sit down on each of these leftover sp3 orbitals and form 6 equivalent carbon-hydrogen bonds. Ethylene is a little more complicated. Let's hybridize a carbon sp2. That means you take 1 s orbital and 2 p orbitals to give 3 sp2 orbitals. You have a remaining p orbital that is perpendicular to the plane of those sp2 orbitals. Once you form this, let's say you have 2 of them, you can overlap those bonds, and we're going to look and see how you can form 2 different bonds between the carbons. So an sp2 hybridized carbon has 1, 2, 3 sp2 orbitals, and this leftover p orbital. There's 1 electron in each of these 4 orbitals. If you turn it on its side, as is shown right here, the p orbital is sticking out of the page, and the 3 sp2 orbitals are in the plane of the page. So this leftover p is perpendicular to the other orbitals. So now what I'm going to do is I'm going to have these 2 sp2 hybridized orbitals come in. So I'm going to bring this and this orbital together, and they're going to overlap and make a sigma bond. Then, when you have those overlap, these 2 p orbitals can overlap in a side-to-side fashion. And when they overlap in the side-to-side fashion, what do we get? We get a pi bond. A pi bond is where it's half above and half below the two atoms that are being bound together. And it's weaker, but it still strengthens the attachment between the two carbons. And it's above and below the two carbons at the same time. Half the bond is above, half the bond is below. And then you have these 4 sp2 hybrid orbitals that are left over, and that's where you'll have one hydrogen sit down on each of these sp2 orbitals. Here's acetylene. One of the carbons in acetylene is going to be sp hybridized. To make an sp hybrid orbital, you take one s and one p, leaving 2 p orbitals left over. This gives 2 sp hybrids, one of them here and one of them here. The 2 p orbitals that are left over, one is perpendicular to these two, and then the other is perpendicular to the other two also. So an sp hybrid, an sp hybrid, one p orbital, and another p orbital. When they overlap, what we're going to do is this is really, the picture here is really hard to follow. But here is one carbon atom. Look right here. What do we see? One p orbital, another p orbital. Here is an sp hybrid, and here is an sp hybrid. Now what we're going to do is we're going to push them together. When we push them together, these two sp hybrids overlap and make a sigma bond. This, and the other half of it is down here and down here. They overlap to form a pi bond. This pink side and this pink side and that blue side and that blue side, they overlap and they form a pi bond. So what you end up with is there's an sp to a hydrogen sigma bond here, an sp to a hydrogen sigma bond here. And what do we have in here? We have a sigma bond that is formed by an sp to sp overlap, and then we have one of those extra bonds is a pi orbital, and then the other bond there is a pi orbital. So there are 2 pi orbitals with the sigma bond. All right, that was a lot of information, wasn't it? I got a summary for you that might help. And then another thing is try the problems in the book, and you're going to see the level of understanding here is not going to be super high. So if you do the problems and you start answering them correctly, you're going to start getting an understanding of what you need to know. Okay, to summarize VSEPR, if you have 2 areas of electron density, the bond angles are 180 degrees. You have a linear electron geometry, and you draw it just like this. What do you have? An sp hybridization with 2 leftover p's, giving 2 pi bonds. So every time you have linear arrangement, the atom that is linear must have sp hybridization and must have 2 pi bonds attached to it, either 2 pi bonds in one direction or 1 pi bond in one side and 1 pi bond on the other side. If you have 3 areas of electron density, you are always going to have 120 degree angles, and it will be a trigonal planar shape, and we draw it like this. This atom here must be sp2 hybridized with a leftover p on it. Either that p is going to be empty, as in the case of aluminum and boron, or it will be forming a pi bond with something. So you just have to look to figure out what it's forming a pi bond with. If you have 4 areas of electron density, the bond angles are 109.5, the electron geometry is tetrahedral, and we have a drawing that looks something like this. It's very hard to draw it this tiny, but we'll be doing some drawing on the board in class. This right here is always going to be sp hybridization. All the p's are used up. There's never a pi orbital. It's all sigma bonds.